Hello everyone, my name is Mobin Vaziri and I want to present the paper with title of Low Cost and Hardware Efficient Implementation of Pooling Layers for Stochastic CNN Accelerators. The authors of the paper are Mobin Vaziri and Hadi Jahanirad from University of Kurdistan. With the astonishing achievements of convolutional neural network accelerators in real-time applications, the deployment of CNNs on hardware has become an attractive matter. Pooling layers in CNNs are employed for reducing the computation of convolutional layers. Nevertheless, their hardware implementation strategy can impact the accuracy and performance of accelerators. This paper presents a novel parallel stochastic computing-based architecture of pooling modules in hardware for stochastic CNN accelerators. With this approach, the SC-based average pooling is reconfigurable with 1.28 times lower power consumption, and the max pooling layer achieves area reduction with the ratio of 4.36. Extending the application of stochastic CNN accelerators in different classification problems is also achieved by implementing AAD pooling with the proposed method. Eventually, the reliability of the proposed method is approved by testing our pooling layers in the VGG16 structure with the CIFAR10 datasets. Deep neural networks, such as convolutional neural networks, have emerged to solve large-scale challenging issues. Significant achievements in computer vision applications make them a point of interest for researchers. Frameworks such as TensorFlow, Cross, and PyTorch make designers eligible to deploy and train their desired neural networks on CPUs and GPUs. Exploiting CNNs for real-time applications demands a high throughput and low-power device. Due to reconfigurability and parallel architecture for execution tasks, FPGAs are now preferred devices for deploying CNNs. Frameworks such as HLS4ML and FIN that implement flexible CNNs on hardware are known as CNN accelerators. Design considerations based on area overhead and latency in CNN accelerators motivated researchers to employ some techniques for reducing the indicated factors. Convolution layers in a CNN utilize most of the area and make bottlenecks based on their timing issues. Vinograd convolution with different strides, which converts the convolution operation to general matrix multiplication, can be a suitable method for reducing the area and power consumption by utilizing more addition instead of multiplication. Pooling layers in CNNs are employed to extract vital data from features and reduce the following convolution layers computation. Kernel size, stride, and sort of pooling layer can affect the accuracy of final stage classification. On account of noted factors for pooling layers, area and accuracy of CNN accelerators are highly dependent on hardware design strategies. Computing techniques such as stochastic computing is an approach to implementing high-cost and complex circuits with simple logic gates and circuits. Low area consumption and fault tolerance compared to the binary field makes stochastic circuits a better choice for designing pooling layers. Stochastic computing, which uses simple logic circuits for calculating multiplication, addition, and division, has shown great prospects for implementing CNN accelerators. In this computing paradigm, numbers are represented by a random string. The most common stochastic numerical formats that have been used are unipolar and bipolar, which we define them in equation 4 and 5. Using the SC elements that we illustrate in figure 1 is related to the application and type of SC numerical format. As depicted in Figure 1 Part G, we need a stochastic number generator to generate a stochastic number stream. SNG is mainly constructed from a linear feedback shift register and a comparator that compares random numbers with the input to generate a stochastic stream. Generated streams run through the elements in Figure 1 and stream out the result. For converting the stochastic streams to binary numbers, a de-randomizer module is used. Despite these advantages in reducing area and power, the SC paradigm has some minor issues. Random seed selection for the LFSR module causes fluctuation error. This error affects the functionality of the SNG module and represents a binary number with a small error. Increasing the length of the stochastic stream minimizes this error. However, the latency of the design should be regarded. As mentioned before, the sort of pooling layer and its hardware realization can be two crucial criteria for stochastic CNN accelerators. Relying on their high accuracy achievements, max pooling and average pooling are the most used pooling layers. As we represented in Figure 2 Part A, the fixed kernel size average pooling implemented in prior studies reduces the usability of this class of pooling in different CNN architectures. Many efforts have been made to reduce the latency of mentioned average pooling with the same architecture using computation skipping, while results in highly correlated outputs. Stochastic-based max pooling circuits in prior studies require large area due to sequential elements in counter-burst and state machines in tonnage based circuit. Limiting accelerators to mentioned pooling layers affects the accuracy and the application of CNNs. Therefore, in this study, the AAD pooling is implemented using stochastic circuits to increase the flexibility of accelerators and demonstrate the SC paradigm strengths. According to discussed constraints and flaws in the prior designs, this paper presents novel and efficient circuits for pooling layers based on stochastic computing techniques. The main contributions of the paper are usability in distinct CNN structures based on reconfigurable implementation, low area overhead hardware realization through exploiting stochastic computing, reliable for edge-based and low-latency devices via parallel architecture design. This section presents the proposed method for implementing mentioned pooling layers in detail. Due to the non-flexible average pooling circuit in the prior scheme, we designed a reconfigurable average pooling layer to be used in different structures. As demonstrated in Figure 3, the input streams are summed up by OR gates and multiplied by the inverse value of kernel size stream with the AND gate. With this structure, instead of dividing the added streams by kernel size, we use inverse operation and multiply them with the inverse value of kernel size stream. By using this configuration, the average pooling with different kernel sizes can be employed in stochastic CNN accelerators. Designing a max pooling layer first requires devising a max function. The circuit illustrated in Figure 4 is an up-down counter that finds its input's maximum value. Instead of single port for counting up and down, the streams go inside the up-down counter concurrently until the enable port is high. As the enable port detects a falling edge, the counter stops counting and the selected input is streamed out on account of the sign bit of the counter's number. Using this module for lengthy stochastic streams can result in high latency. Therefore, we define some checkpoints to solve this issue. As the distribution of stochastic streams is uniform, the maximum stream has a higher probability even in specific sequences. This property gives strength to the circuit to check the sign bit transitions in the early stages and stream out the maximum input. The proposed circuit can be extended and employed for max pooling layer by reusing the circuit with considering the kernel size. Compared to the prior work, the proposed module demands a lesser area and the design latency is significantly reduced with the checkpointing technique. The AD pooling presented in prior studies is designed to solve the drawbacks of prior pooling layers. It can be used in different classification problems and achieve higher accuracy than other pooling methods. Hardware realization of this pooling method in the binary domain requires high-cost circuits such as divider and absolute value function. As shown in Figure 5, Part B, we propose a stochastic circuit for AD pooling which demands low-cost hardware resources. The absolute value of differences between two independent stochastic streams is realized by applying an XOR gate to the streams. Consequently, instead of designing a subtractor and absolute value function, we use an XOR gate in the first stage. In the second stage, the values are added up and divided by 2 for a kernel size of 4. Divider circuits require consuming DSPs to divide two floating point or fixed point numbers in the binary domain. In the stochastic domain, a scaled adder adds two values and divides the added values by 2 concurrently. The proposed circuit requires no DSPs and reduces the area and power notably. Designing and accelerating deep neural networks on hardware requires a system-level modeling tool such as a high-level synthesis tool. In HLS, C-based programming languages are used to describe the behavioral specification of digital systems. The HLS gets a core function and transforms the defined functions into an RTL structure. The HLS provides C-based test benches to accelerate the verification stage in digital system design. Additionally, Q-simulation verifies the functionality of the described systems in HDLs. After the verification stage, the generated Verilog or VHDL codes from the HLS tool can now be synthesized and implemented via placing and routing on FPGA. We define these core functions as pseudocodes and we represented them in algorithm 1, algorithm 2, and algorithm 3. This section presents the hardware implementation results in comparison with the related studies. The proposed modules are described using the C++ programming language in HLS. The HLS tool used in the study is Xilinx Vivado HLS, and the target device is Xilinx Virtex 7 FPGA. We use Python programming language and cross library to define the model and acquire the dataset in the software phase. The flow of evaluating the performance and accuracy of the proposed method is represented in Figure 6 and the quantitative results are provided in Table 1. Prior schemes deploy the stochastic CNN accelerators on ASIC and do not implement the pooling layer modules standalone. As we implement the modules in HLS, the prior schemes are generated in HLS framework for better comparison and presented in Table 2. As illustrated in Figure 6, we use the VGG16 architecture as our CNN model and CFAR10 as the dataset. The generated features are extracted from convolution layers and proceed to software and proposed pooling layers on hardware. To assess the proposed method's accuracy, we use mean squared error criteria and report the results in Table 1. Based on fluctuation error in the SC paradigm, we run this test 10 times and report the average of MSEs. As the MSEs are approximately near zero with different bit stream lengths, we can demonstrate that our proposed method has excellent accuracy to be used in stochastic and even in non-stochastic CNN accelerators. The implemented modules are also compared to the pure C-based pooling layers in Table 2. This paper presents a novel approach to designing pooling layers for stochastic CNN accelerators. According to the impact of pooling layers on classification accuracy, a low-cost and low-power design method is required for real-time based devices. The method we present in this study solves the configurability issue of average pooling with 1.28 times lower power consumption and achieves area reduction with a ratio of 4.36 in the max pooling layer. Due to extending the pooling layer for stochastic CNN accelerators, parallelized AD pooling is designed with the usability in real-time applications, relying on high accuracy achievements in comparison with software results. In future work, we intend to design more sort of pooling layers with the SC circuits and employ the designed pooling layers in non-stochastic CNN accelerators. Thank you for your attention, and I would be glad to hear your questions.